Your answer is 37.90, and this was the most interesting question I've ever gone through it, because it will actually make you realize that to know actually Fermi energy, to calculate all the Fermi energy calculations, what are the equations that you need to remember at any cost for future exam. So I will give you all equations that is required, okay, to remember for future examinations, and what is their meaning, and how can you explore different their variants, and those variants can be also helpful for calculating questions, okay. Because understanding Fermi energy for 1D, 2D, or 0D, 3D system is a good task, because Fermi energy calculation is really important in semiconductors, and semiconductors nowadays in solar cell unit 2D film, in nanowire also you do, okay, in 3D bulk material also you make. So Fermi energy calculation is really important because it is helpful to know where is my donor state, where is my Fermi energy level. So how much energy is required to excite my electron from valence to conduction, or to donor state, or to acceptor state, okay. So what will be my conductivity, and that is really important for my semiconductor. So Fermi energy is really important, okay. So I'll explain you. I have given all data. So this is the well-known expression, right? You all might have remembered this, because in one of the GATE exam, like in 1920, okay, it was asked for 3D material, the density of state is directly proportional to E to the power what? E to the power half. For 2D material like a film, nanofilm, a density of state is directly proportional to E to the power 0, means it is independent of energy. For 1D, that is nanowire, density of state is directly proportional to E to the power minus half. Okay. For quantum dot, it is a function of another function. It is proportional to function of another E. It is not known which function of E. That depends on material to material. If it is carbon quantum dot, then del will be different function of E. Okay, some expression of E we don't know. It depends on dot to dot. Okay, so this G of E is nothing but density of state. There's many way to write density of state. Density of state is rho of E or G of E, your choice, whatever you tell. What exactly it is? It tells you the number of quantum states per unit volume per unit energy. This is so important definition. It will tell you what exactly it means. Number of quantum states means, like d orbital, d subcell, you have 1, 2, 3, 4. We have a 5 orbitals, right? So you can accommodate up to 10 electrons. You will substitute for 1, 1, and 1, and then you substitute another. This is D10, right? D subcell. How many quantum states are there? 10 quantum states. How to define quantum state or energy state, or just an state? How to define that? You define it by 4 quantum numbers: primary quantum to spin quantum number. Even though 3 will match, 4th one will be automatically different, because for up it is plus half, and for down it is minus half. You got my point? So every electron will be having unique quantum numbers of 4 quantum numbers, combination of 4 quantum numbers, from primary azimuthal to angular to spin. Every state means a state will be called as quantum state if it has all 4 quantum numbers not matching with another 4 quantum number of electron. Otherwise, both electron will be known as same. Both will be in the same quantum state. You got my point? This electron will have a quantum state. That means I will have 4 quantum numbers. Is this 4 quantum number will match with only this electron, no other electron. Why? Because if you see for this, it is same orbital. It will match 3 quantum, but 4th will be different. For this, it has completely changed because it is completely different orbital. Anyway, it's quantum between 2 only it will change. This 2 will change. Got the point? Every quantum state has unique 4 quantum numbers. That means every quantum state can be taken by 1 electron. That means number of quantum state is nothing but number of electrons. Each quantum state is taken by each electron. Each orbital is having 2 quantum states or 2 energy states. Okay, understood? 2 states. Okay, now so number of quantum states, that is number of electrons per unit volume per unit energy. What does that mean? When you draw the band, when you draw a band, this band, normally we write bands, energy bands like this. This is conduction, this is valence, but actually it is like this. They will have maximum and minimum. So they are spaced very small energy states. Small energy states are equispaced. Every energy state will be accommodated some, will have quantum state, so it will accommodate some electron. You got my point? That means number of electron in particular in between small energy gap. Small energy gap, we call it a DE. Small energy gap, we call it a unit energy. That means 1 electron volt. In 1 electron volt energy gap, how many quantum states are there? And in that quantum state is called our number of electron is there. That will we call density of state. You got my point? That means if density of state is higher, that means electrons are higher. In a unit volume, that means if you're like, you cannot take the whole sample and you tell you what is density of state. You have to choose one unit volume, is 1 meter cube or 1 centimeter cube. Means 1 centimeter, 1 centimeter long, 1 centimeter wide, and 1 centimeter height. You have a 1 centimeter cube volume. So that is unit volume. In unit volume, you have to choose. You have every atom will have its own energy levels, and then they will perturbed, and then they will create a bands. I hope you know the concept of bands. You can read Callister. So in your band, your energy states are very closely spaced. That's why we call it as a band. So in that space, you have a quantum states. So you have to choose in unit volume how many quantum states are there. That means how many electrons are there. That is called density of state. So density of state is indirectly telling you about number of electrons. Okay. So if you increase the energy, means if you go up in this is my energy. If this is my band structure, okay, this axis will be my energy. My conduction band is always at higher energy level, at lower. For example, see this. If you go up, okay, if you go up, your density of state will start increasing. If you increase E, your number of electrons will start increasing for case of 3D. Okay, but if you go, but it is exactly inversely proportional in case of, it is independent for 2D. Go up, down, it will be remain same. Density of state will not vary. But in case of 1D, if you increase the energy, if you go at higher energy level in your band, you'll get lower number of electrons. That is for 1D. So for 3D, it varies with different function. Okay. So this is a G. If it is now, this is for one energy, one in unit energy. Okay. I can multiply it with total energy. So G of E, I can multiply with, let me choose this small DE. I can multiply with this much energy, D energy. I can get number of electrons per unit volume, for number of electrons per unit volume for D energy state, right? I can integrate, I can get total number of electron per unit volume. If I integrate this small DE, throughout the, up to what? Let me draw different energy levels. Let's say this is top mode field energy EF. At 0 Kelvin, let me assume my temperature is at 0 Kelvin. My temperature is at 0 Kelvin. So my topmost field energy level is EF. So my electron is filled up to EF. So from 0 to EF energy level, because I have chosen DE, I have Dn electrons, right? So for total E, how much electrons? I will integrate from 0 to EF. I can get at 0 Kelvin what is my total number of electron. You got my point? Samjhe ki nahi samjhe? For 1 electron volt, I have this much. For d electron volt, I will multiply. For 5 electron, I have for 1 electron volt, let's say I'm going to 5 electron. For de electron volt, let's say for 6 electron volt, I would say. So that is Z of E into dE is my number of electron in that energy range. Of course, I'm talking about per unit volume. The number of free electron per unit volume is my electron density. Okay, so G of E into D of E is this. And if I integrate from 0 to EF, I can integrate up to EF for if temperature is 0 Kelvin, because I know at 0 Kelvin my EF is nothing but topmost field energy. So here there is no electrons, so there is no need of integrating this. But if the temperature is any random temperature T, then it will be 0 to infinite. But I'm talking about a 0 Kelvin. You can integrate and you can get the total number of electron. So if you know the expression for density of states for all, you can calculate the Fermi energy. Because if you integrate dn, that is G of E into D of E from 0 to EF. So actually, you can know this will give you your n, number of free electron per unit volume for 3D. For 2D, per unit area. For 1D, number per unit length. All are electron density. You can calculate n in terms of EF, because in your limit you have EF. So you can relate Fermi energy with n by integrating this all expression. So important is to remember this expression. It's really important expression. I need to understand this expression. Okay. Now remember that. Now this m, if you notice, this m is it's not the effective mass, it's a rest mass. Okay, it's a rest mass. What is my effective mass? So I'm considering this m as what? I'm considering this m as rest mass of electron. Okay, the moment, remember, the moment your m will approach to m star, that is effective mass, that means my electron is start moving. What is effective mass? Effective mass when electron is not in rest position. If electron will start moving, that means I will only consider my kinetic energy. So what is kinetic energy? That is excess of conduction band. Wait, let me tell you. This is my valence band, and this is my conduction band. This is my conduction band energy, and this is my valence band energy. Got my point? Let's say my energy of electron is this. So this much extra for reaching to the conduction band, it will become free. The moment it will become free, the material, it will have this excess energy will be in form of kinetic energy. So this mass will no longer be rest mass. It will become effective mass that will be slightly lower than the rest mass because of motion. M star is m by root over 1 n minus v square by c square. If you increase the velocity, okay, this rest mass, your actual mass will decrease. This is the theory of relativity from Einstein. So if your material will have energy higher than conduction energy, then what will happen? The material will start have kinetic energy. So your mass will no longer be m. It will be slightly lower than rest mass. Actual mass will be, effective mass will be lower than rest mass. That will be m star. So this m star is coming because of the energy. How much? This much. How much this energy? E minus EC. This, because of this E minus EC, that's the extra. Once it is reached to the conduction band, it is free. So how much extra it is having is the kinetic energy. Because it is free, now the energy will be in form of kinetic energy. So your energy, the moment you replace m with m star, you're only considering kinetic energy. So your energy, which this material is having, this electron is having, is E minus EC. Extra energy as a kinetic energy. So you can replace this E with E minus EC. That's it. So the same expression you can write. If you're writing m as m star, then you can write this E as E minus EC. Okay. So the same expression many author has given in this way also. If you simplify this expression, you will get the same expression, that previous one. You can see if you replace this E minus EC as E, then you can replace this m star as n. then it will become the same expression that I showed in the this one. It will become, you can just do the calculation, okay? It will become this one, this one. You got my point? Both expression is true. This is telling that this is in terms of effective mass and that is the rest mass. Only you need to do is you replace this E with E minus EC. That was E to the power half, na? You have to write E minus EC to the power half, okay? And then we will replace by M star. Then you can get this expression also. It's a similar expression. You can if you remember one, so that G of E expression is important. Okay, this one. If you remember this, that's enough, or more than enough. Now let's calculate. Now let's know the expression, the relation between N and EF, because this is very important. We know relation between G of E, which will give you the number of quantum states per unit volume per unit energy. So you have to multiply with energy and then you have to integrate it so that you will get a number of electron per unit volume or per unit area per unit length, right? So my density state is increasing, and this is for 3D. This graph is for 3D. E to the power half. Okay. This is known as, this area under the curve is known as number of electron. This is mathematics, okay? Like if you can write n equals to integration of rho of E dE, that means if you plot rho of E with E, okay, the area under the curve is, this is Y and this you can take it as a dx. A small strip, you can take it as a dx, right? So Y into dx, if you integrate Y into dx, you'll get the area under the curve. So it's the same thing. So area under the curve is number of electron per unit volume. I will rather use N by V as just N, and my definition, by definition it is number of electron per unit volume. I don't need to write this. N is actually, I should write this N as N dash. This N dash is total number of electron in V value, and if you divide by V, the number of electron per unit volume is N. This is the electron density per unit volume. Okay, so this is the number of electron per unit volume. You got my point? So this is the way you can represent the same thing, integration. But you have to know your N is rho of E D. This is per unit energy, multiply by energy, you'll get the, for that energy, what is the number of electron? Now integrate, you'll get the total electron. Now you can calculate for expression for 3D as well. What is the integrate, and you can get. Let's calculate this number of electron density, that is number of electron per unit volume, and with the rho E. We know the expression of rho E, right? For 3D. For 3D, what is rho E? Rho E is nothing but G, okay? I'm given in G. So what is G? G is what? 8 root 2. I've given in the previous slide. 8 root 2 pi m by HQ e to the power half. You can just integrate it, right? So N is 0 to EF. Why up to EF? Because I am considering at 0 Kelvin, what is the total number of electron per unit volume? Okay, so I will integrate from, I will take this small dE and I will integrate from 0 to EF, because my topmost field energy level is EF in my at 0 Kelvin. Okay, that is by definition. So rho of E is what? 8 root 2 pi m by HQ e to the power half dE, right? And now I can simply integrate it. It will become 8 root 2 pi m to the power 3 by 2. This e to the power will come forward and you'll add plus 1. Okay, plus 1 by n plus 1, right? So you can do that simple derivation. You can get HQ. Okay, and then this, okay, this m to the power 3 by 2. I think I've done a mistake. Okay. This m to the power 3 by 2, e to the power half, you can integrate it 2 by 3, e to the power 3 by 2, right? 0 3 by 2, and then you can put the unit 0 to EF, and then you can simply get 8 root 2 pi m to the power 3 by 2 by HQ into 2 by 3 into EF to the power 3 by 2, and then you can simplify. You can simplify it, and you can get EF equals to h square by. Okay. Now simply you can just put the manipulate the equation. you can simply modify this equation. Please note it down, the final expression that we will get. Okay, that is the formula. You can remember formula, or you can know what is the g of E, and then you can integrate on the spot if you are not able to remember for EF and a relation with the 3D, 2D, and 1D. Okay, so EF, you can simply write EF equals to 3hq ny 16 pi root 2 m to the power 3 by 2 to the power 3 by 2. If you simplify it, your EF will become h square by 8m, okay, 3 by pi to the power 2 by 3. This is the expression, relation between n and EF and n. Okay, this is for 3D. This is called electron density, number of electron per unit volume. If you know, sorry, this is called Fermi energy, and this is the electron density, number of electron per unit volume. If you know number of electron density, you can calculate Fermi energy. Okay, similar you can do exercise for 2D as well. So for 2D, what is my relation between? So 2D, it is independent of energy. It is m by pi h cross square. M by pi h cross square. So just simply write 0 to EF m by pi h cross square. It's very simple. Okay, it's a m by pi h cross square will be common. You're integrating only dE. What is d? It is E. M by pi h cross square. It is e to the power 0 to EF. So what is your final expression? N equals to m by what is m what is EF equals to m by pi h cross square and EF. Simple. See how simple the relation is. Okay, so your EF will be pi h cross square by m into n. This is typical relation for 2D. If you know number, this is number of electron per unit area, because it is 2D. Number of electron per unit area, that means its unit will be centimeter to the power minus 2. Okay, n per unit area, and this is Fermi energy. Similarly, you can do, please note it down this also, or if you know the derivation, you just remember the density of state expression. This expression, your rho of E or G of E is m by pi h cross E. There is no E. If you want to write intensely E, you can write E to the power 0, because it is independent of E. It will become 1. Okay, it will be constant. Now for 1D, that is the question that is asked here in this year question, this year gate. For 1D, what is rho of E? If you see for 1D, what is that? 1 by h cross pi. 1 by h cross pi. Okay, root m by 2e. Right? You can simply put here 1 by h cross pi root m by 2e. So 1 by h cross pi root m by 2e. So 1 by h cross pi root m by 2e. This is your g of E or rho of E. Okay, simply put, and now you'll get the final expression. So 0 to EF, it is, you can modify this, because I want to separate E. So root m by root 2, sorry, h cross pi into root 2, and this E will go at top, it will become e to the power minus half. That's why we, for 1D, rho of E is directly equal to e to the power minus half for 1D. Okay, so you can simply put here root m by h cross pi root 2, okay, and then e to the power minus half dE. So this is just constant, root m by h cross pi root 2, and e to the power minus half. If you integrate, what will you get? It is e to the power minus half plus 1 by minus half plus 1, right? What is the unit? What is the limit? 0 to EF. Now you can simply put the limit. So you'll get root 2 root m. Okay. I mean, you can write, you can simplify, and after simplification, what you will get is root 2 h cross root m h cross pi, because this root m is going to be this root 2 is going to be cancelled out with this 2. Okay, root 2, you can write 2 into 2 equals to root 2 into root 2. So root 2 into m h cross pi e to the power ef to the power half. This is your expression for n. Or for ef, what is the expression? It is for ef, what is the expression? It is n into, sorry, it is h cross pi by root 2 into root m into n, right? And if you simplify it, ef is nothing but h cross by h cross square, of course. It is ef to the power, wait, yeah, of course it will e to the power half, no? So it will become a square. So it becomes h cross square, okay, pi square by 2n square. This is your expression. And if you remember your gate question, h cross square by 2m is already given. So they really don't want you to do this much exercise. This is your final expression for ef and n. Okay, let's go back and solve our gate question. For 0d, since that function is not defined, so you cannot integrate. You got my point? It must be given. If it is given, it is very easy to calculate. This function is not defined, rho of e. So how will you integrate? You got my point? This rho is a function, it's not a value. Don't think like rho into e minus es is given. No, it's a rho of, it's a function f of e minus ec. That is a formula. It's a formula. It's an expression of e minus ec. Okay, that must be given. Then only you'll integrate. Okay, it differs. Let's go to the question. So as you can see, what's the expression? Our EF for 1D, for one dimensional nanowire, EF is h cross. We just solved it. H square pi square by 2m into n square. Simple. As you can see, h cross square by 2m is already given. You can calculate the Fermi energy. In it, of course, it is in electron volt. Then your n, what is n? For 1D, what is n? Number of electron per unit length. Because it is 1D. It is a 1D. There is no volume. There is no area. It's a length. It's a number of electrons per unit length. As you can see, that means meter inverse. It's given centimeter inverse. That means you have to convert it into meter. Then only your energy will come in joule. If n is in meter, h is in joule, h cross is in joule, okay, then ef is in joule. Okay, if h cross is in electron volt, you have to convert it into joule. Why? Because if you are putting h cross value, h square, like you can write now, h cross square by 2m into pi square n square. Like if you're putting h cross 2 by into the see, it is in electron volt, and this is in second kg. So this is in SI, this is in SI, and this is in SI, and this is not SI. So you have to convert into joule. Then only this whole quantity is in SI, international system. You can convert this n into SI in meter. Then your EF will come in meter, in joule, and then later on you can convert into electron. So a small dimensional trick is given. You got my point? You cannot have mix of two different systems. You have to convert this electron volt into joule. And because this is already in SI system, this is already in SI system, then definitely this N must be in SI system. Then automatically you'll get J in SI, EF in SI system in joule. And then you can convert later into electron. Okay, you got my point? So it's a simple calculation, you can do it. Okay. So let me just do it. So your EF is, so let me just write, number of electron is 10 power 8 centimeter inverse. That means 10 power 8 per centimeter. That means 10 power 8 centimeter. I can write 10 power minus 2 meter. So it's a 10 power 8 into 10 power 2 meter inverse. That is 10 power 10 meter inverse. N is 10 power 10 meter inverse. Let me also convert this h cross square by 2m into joule. So 0.25 electron volt square. So I can put electron volt equals to joule. So 1 electron volt is 1.6 into 10 power minus 19 joule. I can put here 1.6 into 10 power minus 19 joule to the power whole square. So to the power whole square. What I've replaced this electron volt with the joule to the power whole square. Then second square kg inverse. Simple. So my 0.24 into it is 1.6 into 10 power minus 19 ka whole square. It is 1.6 square into 10 power minus 19 square, that is 38, and it will become joule square second square kg inverse. Now everything is in SI. So my h cross square by 2m is also in joule and SI. Now I can put here, I can get my EF. What is my EF? H cross square by 2m. See, if you remember this now, you don't need to do the derivation also. Your mind will tell, oh, h cross square by 2m, and what was the rest? Rest is pi square n square. Right? So this is already given. How much? 0.24 into 1.6 square into 10 power minus 38 into pi square into n square. N is what? 10 power 10 to 10 power 10 ka whole square. Simple. Ho gaya solution. Whatever you will get is 6.0638 into 10 power minus 18 joule. Okay. Convert, and it's asking in electron volt. So convert into electron volt. Divide this by 1.6 into 10 power minus 19. Your answer will come in. Your answer will come in 37.899. This is your typical EF. So I hope from this demonstration you know what is density of state, how density of state is giving you number of electrons, and how density of states can be converted into number of electron with the help of integration. How you can establish the relation between Fermi energy and electron density for 1D, 2D, and 3D. Of course, 0D you cannot do because 0D depends on function delta that must be given. The expression must be given. Okay. So I hope it's clear to everyone. Now, any question which will be asked from this topic, you'll be able to solve it. The next question is from the isothermal process. What is the work done? So what is isothermal process? So your dW is, sorry, your heat is work done. Sorry, how much internal energy is changed? First law, if you see. Okay, let me write what is given. The number of moles, N is given 2 moles. P1 is given as 10 atm. T1 is given as 300 Kelvin. Similarly, P2 is isothermally. So you can change the pressure to 2 atm, and your pressure remains the same because it is isothermally and of course reversible. Any formula that you derive, it is only for reversible. Okay, for irreversible, it's not easy. All the process should be reversible. I hope you understand this all concept from thermodynamics. This is basics. Okay, so for reversibly, and of course thermic T2 is also same. And absolute work done, what is W? So if you see from the first law of thermodynamics, dq is what? Change in internal energy, and plus remaining whatever the heat you will get, it will increase internal energy, increase its temperature, and plus it is internal energy, and remaining will do the work. So du plus pdv. Okay, dq. Okay, now if it is isothermal process, isothermal is temperature is constant. Remember, this internal energy is only function of temperature, nothing else. If temperature is constant, that means U2 minus U1 will become 0. Because temperature is not changing, U will not change, internal energy will not change. That means internal energy will not change, and dV will become 0. If this will become 0, your dq will be dTV. Right? So your work done will be, all the heat that you have given is converted into work, and your work done is PVT. So your work done is PdV. So dW. Your work done is PdV. You can integrate it from. So if you see PdV, by seeing the expression PdV, what do you recall? By dx, it's the area under the curve. What do you recall? Y is your P, and dx is your volume. So this is typical isothermal PV graph. Area under the curve, area of the curve is the work done from volume from V1 to V2. So your from V1 to V2, you have to integrate. This will be W. This will give you P, and it will give you, of course, see, P is function of volume, because if you're changing the pressure, you're changing volume, right? So you can write P in terms of V, because we need, if P is function of V, you have to put P in terms of V so that you can integrate. Huh? So your PV equals to nRT, right? So your V will be nRT by T. Sorry, I need P. So P equals to nRT by V. So I can put here P equals to nRT by V. See, my P is a function of V. Of course, P is a function of V. I should not take P as a constant, because it's changing with V. I should write P in terms of V so that I can integrate. So nRT will be outside N1 by V dV. Why I'm telling this all? Because you should not memorize formula at all. If you keep memorizing, there is a lot of process. Because if I were there at the place of you, and I don't remember the work done formula for isothermal process, I will not panic. Because I know PV graph. I know what is work done. It is area under the curve. It is nothing but integration of PdV. I know I will simply integrate. I will find my formula, even though I don't remember in the exam. So that is why I always motivate my students. Don't, even if you memorize formula, it's good. It will give you pace in your GATE exam. It will give you speed in your GATE exam. But always understand the process and derivation, so that if somehow I'm teaching this in my regular class, and somehow it is not touched in your test series, or it took a lot of gap, you didn't revise and you forgot formula. Suddenly it came to your exam. What will you do? You should know the process. You should simply derive it. It's not a rocket science. And then you can solve any question. Got my point? So now see, it's very basic. You can find your formula. What is formula? 1 by V dV. What is the integration of 1 by V? From V1 to V2. 1 by V is ln V. So it is nRT ln V from V1 to V2. It is nothing but nRT ln V2 minus V1. That is V2 by V1. This is work done. Very simple. If it is isothermal, then PV equals to constant. Boyle's law. That means P1 V1 equals to V2 V2. Why I need this? Because V2 by V1 is not given. P2 by P1 is given. I can write my V2 by V1 is what? P1 by P2. This formula can also be written as nRT ln P1 by P2. Simple for isothermal. Simply. Now it's just put here. N is 2 mole, R is 8.314, T is how much? What is 300 Kelvin? ln P1 is what? P1 is 10 ATM. Why I'm writing ATM? I'll tell you what. This is 2 ATM. Since C, oof, I'm done. Sorry guys. I cannot also reverse it. I'm really sorry. Okay, so your work done is nRT ln P1 by P2. So your N is 2, R is 8.314 into T is 300 Kelvin, ln P1 is 10 ATM and 2 ATM. Why I'm writing ATM is, see, this is a ratio. ATM will get cancelled. So even though it is given 1 ATM equals to conversion, you don't need to convert it. Got my point? Because your P1 by P2 is in ratio, there is no other P in this area. So that if you're using R in mole, then this should be in Pascal, ATM. Or it should be in the SI system. Pascal. Don't need to, because it's considered. You don't need to convert, okay? So you get 2 into 8.314 into 300 ln 5. You solve this, this will give you answer. So what is answer? I think I didn't show you answer, guys. It is 8.31. Sorry, 8.03. Okay. What is this answer? Answer is 5.63. Okay. How to solve it? It's very easy. It's actually from directly Nernst equation. It's not a rocket science. Okay, so if you see what is given for it, so the given is what is given. So it is given that your zinc is solid and it is yeah, hydrogen is reducing to oxidize zinc. This is redox reaction. Okay, your H2 is a gas. The actually half reactions will be zinc will be oxidized to Zn2 plus 2 electron, and your hydrogen will be reduced. So ultimately you'll get zinc plus 2H plus Zn2 plus H2. This one. So what is next equation for this? So E cell equals to E naught cell minus, at room temperature it's not given, so let me write the whole expression. RT by NF. I don't need to write 2.33 because in your question it is given calculate ln product is what? Zn2 plus. This is a gas, so you must write this. Gas you have to write in form of partial pressure. If it is metal, like let's say copper solid, then you don't need to write. You only need this. Okay, it is a gas. You must write gas because it is a partial. This gas will have partial pressure of it. Since it has a coefficient 1, so I cannot write power. Power will be 1. Product by reactant. What is reactant? So H plus is my, it has coefficient 2, so H square. I can write coefficient of Z. It's a solid, so it has activity 1, so it has composition 1, so I don't need to write. Actually, in your question, if you see, it is asked to calculate ln Zn2 plus by H plus square, right? So that is why, if this is getting asked, so that is why I have written in form ln. I have not written 2.303 RT by log. You can write, and then later on you can calculate this, and you can write ln also. But this is what this straightforward. Okay, this P of HQ. So what is given? Your E cell is given, that is 0.690 volt, and your partial pressure of hydrogen is given 1 atm. Temperature is given 298 Kelvin. So it's very risky to write 0.0592 because then it will become log. I want to make it ln because I want to calculate the same thing. But my point. So let's write RT whole. RT, and your, I think RT by F is also given. It's very easy then, 0.0256 volt. And standard potential for both electrode is also given for Zn2 plus. So SHE is given as minus 0.762 standard hydrogen potential electrode, and with respect to standard hydrogen electrode, and E naught for hydrogen, it's a 0. If you all know, it's a reference. So I think you want to, the PHQ is given as 1 atm. So anyway, this is not a factor, it becomes 1. So this is what they are asking to calculate, and everything is given. Just put, you will get your answer. Everything is given. What is E cell? E cell is E naught cathode minus E naught anode. What is cathode? What is anode? So something which has higher reduction potential will be more, will have more tendency to reduce because it has higher reduction potential. So this has higher reduction potential, hydrogen electrode. So it will be cathode. It will reduce more. This will be oxidized. It will be anode. So cathode minus anode. So that is 0 minus 0.762. Right? You can simply, and this R is, see, RT by N is also given. Sorry, RT by F. Sorry, RT by F is already given, and N is also, no, you know, it is 2 electrons. It's 2, and E cell is already given. This you can already calculate. You can calculate your ln. That how much you'll get? 5.625. Okay, ln Zn2 plus by H plus square. Now this is your answer. Now the next question is, this one was also very interesting, because it was completely new concept. Okay, if one really understand what is the concept behind observing different Raman lines, whether it is anti-Stokes or Stokes, both are Raman line only. What is the concept behind it? Okay, if you really understand, then you can easily write the expression for ratio. It's very easy. Okay, so let's understand what is Raman spectroscopy, what is it based on, and what is the concept behind getting Raman lines. Okay, and then you can relate how intensity can be derived, and it's a very basic expression. Okay, even though it is not written in any book, if you know the concept, you can write within fraction of a second. And by seeing the unit also, it somehow it will be related to Boltzmann distribution. So let's go and understand first. Okay, let me write the answer first. Answer is 0.338. If some of you have attempted, you can see. So what is Raman spectroscopy? In Raman spectroscopy, basically every molecule have their own vibrational modes. Means if you put some vibration, if you put some photons, or if you put some laser, that molecule will absorb that energy of that laser or photon, and it will vibrate according to its different vibrational mode. So depending on its vibration mode, it will absorb some of the photon energy, and then later on it will emit that energy, radiate that energy in form of photon. Okay, so that means the energy that is radiated, or the wavelength of photon that is radiated, okay, will give you the spectrum. If you can track that, like for example, I have excitation laser, and that is giving you around 600 nanometer. I have a laser that is giving you energy hnu, and that is equivalent to 600 nanometer wavelength. Of course, you can calculate what is the energy, corresponding energy. 700 is around 3.1 electron volts. It will be somewhere 2.5 electron volt. Okay, let's say I'm giving 2.5 electron volt energy. What this molecule will absorb some of the energy. If it is at ground state, it will absorb some of the energy. Okay, and it will absorb some of the energy. So if it is at ground state, it will absorb some of the energy. It will go to the different vibrational mode. And since it has absorbed some of the energy from ground state to excited state, it will absorb some of the energy. So it will radiate the photon which have slightly lower energy, because some of the energy is absorbed by molecule, because it was already at ground state. To excite that, it absorbs some of the energy, rest of the energy is radiated. This process is called scattering. So you have two type of scattering. If electron is interacting with matter, or if a photon is interacting with matter, in both cases you're scattering. If one ball is colliding with another ball, all kind of scattering can be divided into two parts. One is elastic, one is inelastic. Here in this case, it is inelastic. Why? Because some energy is lost. Because I'm giving, let's say, 2.5 electron volt. I gave 2.5 electron volt, this much long. It excited this much long. The gap is equivalent to the 2.5 electron volt. Now it is giving this much only. This much is absorbed. So this hnu is always less than 2.5 electron volt. So some of the energy is lost. This coming and this going. Like you have one ball here, one ball is striking, then one ball went here and one ball went here. So if your total energy is this energy, kinetic energy of this and kinetic energy of this, if you combine it, total energy, if it is less than energy of this, I'm assuming this as a rest state. If the incident energy is not equal to the final energy, then some of the energy is lost in the collision. That is called inelastic collision. So momentum is conserved, but energy is lost. So that is inelastic. So most of the scattering will be always inelastic. So in the inelastic energy is not conserved, momentum is conserved. In Raman spectroscopy, those scattering, inelastic scattering, those scattering is called Raman scattering. Okay, like this is my different vibrational mode. If my electron is here, it is excited to there, and then it come back to same energy state. So I'm giving hnu energy, and my after scattering, my energy is hnu only. So there is no energy absorbed or lost. It is called elastic scattering. And this scattering you get in form of Rayleigh scattering. Like most of the laser photons will go and strike the molecule, and the energy that molecule will vibrate. So the photon energy will convert into phonon, and later on phonon will convert into photon. So the final photon and initial photon will have the same energy. It is called Rayleigh scattering. So this is not our concern. We always try to filter it out, because this will not give you the how much energy is absorbed or emitted from the system. That will be characteristic to their vibrational mode of molecule, and that is characteristic to the that is fingerprint for that molecule. So we can identify for particular how much energy is absorbed, okay, can be related to how much, what is the that will be a fingerprint for particular molecule, because every molecule has different vibrational modes. So that means I know if my how much energy is absorbed, or how much energy is decreased or increased, or how much Raman line is shifted by Raman shift or by increase or decrease in energy. I can tell like, oh, if it is decreasing by 0.1 electron volt, that means 0.1 electron volt is unique and is only coming from this organic molecule. So this is the material is having this organic molecule. So we can use it as a structural fingerprint to identify the molecule. Got my point? Later on, we'll see what are the different increase in energy, decrease in energy, and so our Rayleigh is not our concern. Our concern is Raman, energy lost, either it is increased or decreased, energy lost in the system, Raman. That is our concern. Okay, so we filter it out. So if you see the process chart, vibrated molecules will give you Rayleigh scattering. We try to filter it out using edge filter. We only take Raman scattering, means photons which has either lower energy than the incident energy or the higher energy than incident energy. When will you get higher energy? For example, your molecule is already at higher energy state, because you increase your temperature of your molecule, like you are doing Raman spectroscopy at room temperature, or you're doing the Raman spectroscopy at 100 degrees Celsius. Definitely at 100 degrees Celsius, molecule is already at vibrating, already at high energy state. Now, if you're giving your laser, which is having HNU energy, okay, so what will happen? Your atom is already here. Let's say it is excited this much, depending on how much HNU you gave. Okay, got my point? When it will come to the ground state, it will give you more energy. That energy is the extra energy that is added due to extra thermal energy that it has, because it was already having some energy. So that molecule is already having, let's say, 1 electron volt, and you give 2 electron volt. So the final photon that you will get will have 3 electron. The gap will be higher. So that means your scattered photon can have a higher energy, because the molecule was already at higher energy state. So that energy is added to the final scattered photons, and you get a higher. That is the case. That is also Raman scattering. Okay. So if your energy of the laser photon shifted up, means it increases. That means your molecule was already at excited state. We call it as an anti-Stokes line. If the energy is shifted down, means your molecule was already at ground state. So it takes the energy to go to the excited, and then it come back. So the scattered photon has lower energy than the incident. That means the energy of the photon is decreased. Laser photons shifted down. It's called Stokes line. And actually, if you remember, normally in a spectroscopy language, Raman spectroscopy, our energy is hν or hc by lambda. Okay, so hc is a constant. So what we do is we can write E is directly proportional to 1 by lambda. We take this 1 by lambda as wave number nu bar. This wave number is nothing but 1 by lambda. This wave number is a representation of energy. Higher the wave number, higher the energy. Higher the wave number, higher 1 by lambda. Of course, you have to multiply by hc, you'll get energy. So wave number is a kind of representation of energy. It's not exactly energy. Please understand. Your wave number is 1 by lambda. So your energy will be hc by lambda. So hc into 1 by lambda. So hc into 1 by lambda is nu bar. So your wave number is not energy, but higher the wave number, higher is the energy. You got the point? So we do conversation in form of wave number. Remember, higher the wave number, higher the energy. Now in this case, Stokes line will have lower wave number. So let's say my incident laser has nu naught frequency. After colliding, the laser photon has energy lower than that nu naught. So nu naught minus nu. We call it as a what? Stokes line. This scattering will be called as Raman scattering. The Raman line is called, which Raman line is this? Stokes line, which is observed at frequency nu naught minus nu. Current frequency is this much. It has this much energy is changed. Nu is the shift. Okay. Now it has already some energy, so that energy will be added. Okay. This is called Anti-Stokes line, that is shifted up. Anti-Stokes line. This is also a Raman line which has higher energy than the incident one. So if you plot, so this is your typical at nu naught, the frequency of this is frequency at incident laser photon. Higher than nu naught will be anti-Stokes. This frequency will be how much? Nu naught plus nu. And lower than nu naught, this is Stokes. It will be nu naught minus nu. As you can see, this is what it's with. If you plot with frequency, this is what you will get. Got my point? So this graph is something that is telling you. And if the incident frequency is same as scattered frequency, then it is not Raman scattering, it is Rayleigh scattering, and we are not interested in that, because it is telling nothing about vibrational mode of molecules. It's not telling anything about which molecule is present there. Okay, so now let's go to the much deeper. So the intensity of a Stokes line, intensity is an anti-Stokes line at ordinary temperature. So what is Stokes line? Due to excitation of atom from the ground to excited state. If you see here, this is the atom is at my ground state, and it excited to a excited state. Now when it is coming back, see this gap is higher, so energy is higher, so incident is higher because it jumped to this much height. This height is telling you about energy, and it is this, whenever it will come down, it will emit energy. That since the gap is lower, energy is lower. Something is absorbed. Okay, so that is called Stokes. In NT, or it is already at a higher energy state. So this is the given incident energy. This gap is telling incident energy. When it will come back to the ground, it is adding extra energy. It is giving that was already available from on the system. So total energy is higher. This gap is higher. That is the anti-Stokes. Okay. So what do you observe from here? You can observe here. So your anti-Stokes is coming at higher frequency, and Stokes is coming at lower frequency. Rayleigh is exactly the same frequency of nu naught. That is the incident frequency. We are not interested in Rayleigh. Okay. So due to excitation of atoms from the ground states. So you have atoms at ground states. So let me draw that. So higher the atoms at ground state, more will be intensity of Stokes line. Got my mind? Because higher the atoms at ground state, more atom will excite to the higher energy, and more more excited will come to the ground. So more emission will be there. So more Stokes line will be created. So more intensity will be there. You got my point? So higher the atoms in the ground state, more will be intensity for Stokes line. And if you see the previous, if you see, if you see, your Stokes line is always bigger than the NT. This intensity is always bigger than NT. Why? The reason is normally in our molecule, at ordinary temperature, the molecules are, most of the molecules are at ground state. If number of molecules at ground state is very high, then because that Stokes line is created because of atoms exciting from ground state, not the excited state. So more the atom at ground state, more will be this kind of transition. So more will be photons. More will be photons means more will be intensity. What is intensity? How much energy per unit area per unit time. Energy per unit area is power per unit time. Power per unit time is intensity. So energy is your h nu. And let's say you have n photons, n into h nu by AT. So higher the number of photon, more will be intensity. How will you get more photons? So one molecule is excited and then it came down, you created one photon. So more the atoms will be at ground state, more this transition will occur. More number of photon will create it. More photon will be created, more intensity. More intensity. Got my point? Okay. So I can write for anti-Stokes line due to transition of the atoms from excited to ground. So it will have a, so intensity of line will be based on the number of directly proportional to number of atoms in the excited state. What is N1 and N2? N1 is number of atoms in ground state, N2 is number of atoms in excited state. So now here is a point. If you have two energy level, if you remember the questions we solved in lasers, like in one pulse, how many photons will be generated or how much energy will be. Like if the 2 electron volt is the energy is released in single pulse, then how many photons will be generated? Number of photons. So we dope the number of atoms in different energy levels. Let's say this is at first energy level, number of atoms is or atom or molecule is N1. At higher energy level, number of molecules is N2. At more higher energy, number of atoms is N3. So different atoms are doped in my laser at different energy level. Okay. So how many atoms are there in this energy level? Who will decide that? Is given by Boltzmann distribution. So the probability of finding N1 number of atom in even energy state is e to the power P naught, e to the power minus E1 by KT. So similarly, N1 will be N naught, e to the power minus E1 by KT. Okay, it's a simple Boltzmann distribution that we all know. Okay, so let's say N1 is my number of atom at energy level E1, and N2 is my number of atom energy level E2. So and the gap is, let's say, delta E, that is E2 minus E1. How many photon will be created? Number of photon will be generated by N2 minus N1 by 2. This number of photon. And how much? So how many? So total energy. The total energy. So one photon will generate how much energy? Delta E. So let's say n number of photon is there. So n into delta E will be total energy generated. And delta E is nothing but h nu. So total energy released or generated is n into h nu. N is number of photon, that is n2 minus n1 by 2. N2 minus n1 by 2 h nu. This is the energy released in single pulse in laser. If you have n1 atom or molecule at lower energy level, n2 at higher energy level, and n2 minus n1 by 2 is your number of photons, and h nu is the energy of each photon. You got my point? How this is n2 minus 1 by 2 is the that? See, there is a inversion of equilibrium. What is equilibrium? Equilibrium says ki your number of atom here and number of atom here is same. Then they will cancel each other. So let's say you have 100 and here you have 200. And what is the so if n1 is n2 is greater than n1, n3 is greater than n2. If n4 is greater than n3, n3 is greater than n2, n2 is greater than n1, like more number of atom is doped at higher energy level, you'll get laser. Your photon will be will be more in the higher energy levels. They will come down and they will create a lot of h nu or photons. So very coherent photons in same direction is laser. So 100 will cancel out 100. Okay. Now to generate each photon, you need 2 atoms, 1 electron and 1 hole in annihilation. Right. So 200 minus 100, 100 is already cancelled out. So remaining is only 100. 100 is in equilibrium with 100. So this is already cancelled out. remaining is only 100. Now 100 atoms are there, and for each photon we need to have 2 atom or one electron and one hole annihilation. So that is 100 by 2. How will you get? 200 minus 100 by 2. That is N2 minus N1 by 2. This is typically for laser case. Why I'm telling this? Because in laser case you can calculate, use this concept. Here there also we need Boltzmann distribution. Anywhere when you need you are pumping atoms or molecules in different energy level, in typically gas laser like helium neon laser. Okay, there you are pumping helium and neon at different energy level, so definitely you can use this kind of calculation. Here also we are doing the same thing. Like in our molecule, in our, let's say we have a sample have a millions of molecules. Now if it is at high energy level, that molecule, individual molecule are at high energy level and some are at ground state. So how many of them will be in ground state and how many of them will be in the excited state? Who will decide? It will be decided Boltzmann principle only, Boltzmann distribution that is used in laser. Here also the same concept. Ni is n naught e to the power minus ei by kt, or n1 is n naught e to the power minus e1 by kt, or n2. Now I think you guys might have understood what is the ratio of Stokes with anti-Stokes. So I Stokes by I anti-Stokes is nothing but N1 by N2. How? Here I can write I Stokes equals to K N1. Here I can write I anti-Stokes equals to K N2. I can divide, K will be cancelled out. And what is N2 by N1? N1 by N2? What is N1 by N2? You can calculate here. E to the power minus E1 by K. Of course, it will be delta E. It will be delta E. That is, it is similar to the diffusion or vacancy question. Okay, delta E by K, 1 by T1 minus 1 by T2. Simple. This was a typical thing. So you can calculate that question, gate question, from the Boltzmann distribution. N1 by N2, that e to the power minus delta E by KT. Okay, wait. I think I wrote previous expression as in terms of T1, T2. That is wrong because we're not changing temperature. Sorry. So your temperature is constant. Here also your temperature T, and here also your temperature is T. So it's simple. N1 by N2 is nothing but e to the power minus delta E by KT. Delta E is h nu, e to the power minus h nu by KT. And what is your Stokes by anti-Stokes? What is this nu? Nu is the frequency at which Raman line is absorbed. Which line we don't know. Whether it is Stokes or in anti-Stokes, we don't know. Okay, it will be defined by question. The situation might have should be given to know whether that Raman line is Stokes or anti-Stokes. Okay, but it will be observed at particular frequency nu. Then your ratio will be this. Okay, so your final expression, please note it down. This one, it's very simple. Now one thing you remember, in intensity of Stokes line will always be higher than anti-Stokes line at ordinary. The reason is number of atom at ground will be always much more than the excited state at ordinary temperature. Okay. After considering Rayleigh scattering, here we are not considering any Rayleigh scattering. We are thinking like only Raman scattering is observed. There is no Rayleigh scattering because we are actually filtering out all the Rayleigh scattering, that is elastic scattering. But if you consider that, we can get more accurate answer. So this is considering the factor of Raman scattering, where nu is the frequency at frequency of your Raman line, nu naught is the incident frequency. Okay. So your gate question can be solved using this one. There is no mention of incident frequency and all. Okay. Means the incident frequency not given, so you don't need to consider that. So you can solve using this also. Anyway, so I have already given. Okay, this one. So what is nu naught minus nu? Frequency of Stokes line. So Stokes line will always be energy. Stokes line is something when your atom is exciting from ground state, so it will absorb some energy. So finally, photon energy will be lower. How much lower? Your frequency will be lower. How much lower? By nu. Okay. anti-Stokes, it will be added. This is incident, and this is nothing but transition frequency at which Raman line is observed. Okay, Raman scattering frequency. It could be Stoke or anti-Stoke. Okay. Now, if you see the graph, okay, this is intensity with the frequency. The anti-Stoke is here. It is observed at high frequency as compared to incident frequency of incident laser photon, and Stoke is observed at lower frequency. If you can somehow make this at 0, like let's say this is 1000, let's say this is 1000, and this you are getting, let's say 1050, and this you are getting 950, for example. So you can normalize it. You can take it as, so by knowing also, you know, your new K is 50, right? Your new A is 50, and here your new K is 50. Got my point? If you make this as 0, make it as 0. Assume that your Rayleigh scattering is observing at 0. Then this will be 50, and this will be minus 50. This is called shift, Raman shift, in terms of frequency. This is frequency of anti-Stokes line, and this is frequency of Stokes line. Now, if you know nu is 50 for anti-Stokes line, so what will be nu is what? C by lambda. So C by lambda is 50. That means 1 by lambda is 50 by C. Got my point? H in nu equals to H C by lambda. Nu equals to C by lambda. Yeah, that's correct. No? So 1 by lambda is 50 by C. So this is nothing but wave number of anti-Stokes line. Right? Got my point? So for this corresponding 50, I can write my wave number also. Some number here. And the same will be in negative form. So let's say wave number is nu bar of Stokes anti-Stokes line, and this is a nu bar of Stokes line. So if it is, let's say, this number nu bar or wave number or 1 by lambda value, if it is let's say 500, and this, let's say, it is 500, then what is the Raman shift? It is 500 Raman shift. Wave number Raman shift is 500. Okay, I will show you the actual graph how we will observe in a Raman. So this is Rayleigh incident frequency exactly equal to the scattered frequency. This is anti-Stokes line, which will be scattered one. Means after scattering, what is the frequency of your photons? It will be higher than the incident because energy the atoms are already at excited state, so it will add. Stokes line, the after scattering, the frequency of the photon will be lower than the incident because some of the frequency or energy is absorbed. Now, so what we have observed it, Rayleigh height of excitation and the decay is 0, same. So there is no emission. And anti-Stokes, so atoms are already at excited state, so it will be observed at higher frequency, or it will shift off at higher wave number. Higher energy means higher wave number, and here it is already grounded. It is absorbed some of the energy. It will observe at lower frequency, so lower wave number, lower wave number means it will be it will be. So this is assume this as a Rayleigh scattering. Now I'm not plotting with respect to lambda. I'm plotting mu. I'm not. This is with respect to frequency. Okay. So remember. So see. So here you see. Sorry. This is with respect to wave number Raman shift. Okay, we'll come here. This is with respect to lambda. Previously, I was telling about frequency. You got the point. This graph is with respect to frequency. So your anti-Stoke was at right and Stoke was at left. When you plot with lambda, because your nu equals to C by lambda, inversely proportional. There is Stoke will be observed here and anti-Stoke will come here. They will switch because they are inversely relative. So that's why higher frequency means lower wavelength. Okay. So that is what you're saying. Your Stoke is now you're observing here. But remember, your Stoke will be always bigger than the anti-Stoke. The reason is more atoms at ground state. See, so if I'm plotting with respect to lambda, then this is lambda of Stokes, this is lambda of anti-Stokes, and this is the Rayleigh scattered photon. The wavelength of Rayleigh scattered photon, that is nothing but wavelength of incident photon, because it's same. Now see, the photon of the in anti-Stoke, you see, wavelength is observed, wavelength is lower because energy of that anti-Stokes line is higher. So because your energy is hc by lambda, if energy is higher, wavelength will be lower. It will be observed at lower wavelength. Okay. So in Stokes, it will be observed at higher wavelength. If I'm not plotting with lambda, imagine I'm plotting with 1 by lambda. That is nothing but wave number in centimeter inverse. If I'm plotting with respect to wave number, which is the reverse of lambda, what will happen? What will happen? So for example, you see here. So how much is the shift from the Rayleigh? I can assume this as 0. As you can see, it is assumed here. It is actually this is actual Raman spectroscopy image of a sample. Which sample? 2-bromo, 2-methyl propane. Okay. So see here, this is Raman. So this much is the shift. How can you calculate? You know the lambda value. So you can you know the lambda, how much is the from lambda how much is shifted. So you can calculate 1 by lambda naught is my wave number of Rayleigh. That is the incident one, minus, because in anti-Stokes, what will happen? Minus 1 by lambda of anti. It will be negative because your anti is having more nu bar. Your anti means anti-Stokes will give you more energy, higher energy at higher frequency. So higher energy, that means higher wave number. Okay, so that is why incident wave number minus anti-Stokes wave number will always become negative. So that is what you are seeing. It's coming negative. As you can see, it's coming negative. What the point? Your Stokes have always lower wave number. Why? Because Stokes is already, see, Stokes is already at ground state. It's giving you very less energy as compared to the incident because it is some energy is observed. So less energy, that means less nu bar. Right? Energy is directly related to nu bar. You got my point? Less frequency, less nu bar. Less nu bar means less wave number. So since this wave number is lower than the incident, okay, it will come you positive. Okay. So your Raman shift is how much? Incident minus Stokes. Always it will come you negative because Stokes will have Stokes is always lower than the incident. So wave number of incident, so it will positive. And incident minus anti-Stokes. Anti-Stokes will have higher energy or higher wave number, so it will be negative. Okay, where your nu bar is wave number 1 by lambda. I hope you all guys understood. Remember that. Why this will be anti-Stokes line? Because your shift is up, your wave number is higher. This 300, you have 2 Stokes lines. This wait minute guys. This 300, you see here, this 3 now here is the point, very important point. This 300, you see, it's a 1 by lambda value for Stokes. 1 by lambda Stokes, right? So you can, that is nu bar for Stokes. That means you can calculate your energy hc nu bar. Okay, and anti-Stokes line, you see, it's a negative. What my point? Why it's negative? Because its energy is higher. So incident minus energy, this energy is higher. So incident minus this will become negative. Okay, I hope you all understood it. Okay, so this understanding is really important. This is a real what do you call it? So in Raman spectroscopy, we plot intensity versus Raman shift. Always remember, Raman shift is, let's say only one peak is given. So that means your Raman shift is what? Wave number. This Raman shift is wave number. That is 1 by lambda. So wave number for for Anti-Stokes line. Anti-Stokes is minus 300. Let me take only one peak. And let's take this peak. Wave number of Stokes line is 300. What is this? Cm inverse? Cm inverse. That means here, from here, you can calculate 1 by lambda Anti-Stokes is given as minus 300. Remember, it is in centimeter inverse. And from here, you can calculate wavelength of Stokes line. At which wavelength? So 1 by lambda Stokes is equal to 300. If you know lambda, you can calculate their corresponding nu, because nu is C by lambda. So you can calculate nu, and then you can calculate energy. Okay. So I hope you all understood it. Now so this is all concept about Raman spectroscopy. I hope now you have a good idea what is Raman shift, what is intensity ratio, how they are related. Okay, now let's solve the gate question. So if you see the gate question, where is that? So here you are in a Raman spectroscopy excitation done at 300 Kelvin. So T is given as 300 Kelvin. Boltzmann constant is also given 8.62 into 10 power minus 5 electron volt per Kelvin. The ratio of intensity of Stokes to NT. So Stokes by Anti-Stokes is what? We all know, e to the power minus delta E by KT. E to the power minus H nu by, right? Now it's telling Raman line. Which line we don't know. Since it is positive, that means it's definitely what? Stokes line. So Raman line is observed at 200 centimeter inverse. That means 1 by lambda for Stokes, or just 1 by lambda is given as 200 centimeter. So what will you see by lambda? C into 200 centimeter inverse. This is in centimeter inverse. If you're using C in meter, then this must be in meter. You got my point? So this is nu. You can calculate nu. So 200 centimeter inverse is your wave number. Raman is observed at this much wave number. Okay, 200 centimeters. So you can convert it into meter. So 200 divided by centimeter, I can replace 200 by centimeter. I can write 10 power minus 2 meter. That means 200 into 10 power 2 meter inverse, or 2 into 10 power 4 meter inverse. Then I can write 200 is nothing but 2 into 10 power 4 meter inverse. So that will give you simply C into 2 into 10 power 4 meter inverse. That is 3 into 10 power 8, right? Into 2 into 10 power 4. And C has meter per second, and this is divided by meter. Meter is cancelled out. It's a per second. It's a per second. That is typical unit for frequency. You calculated your nu. You put here. Again, you need to know what is the value of H. Actually, if you put this nu and put value of H, okay, in H in electron volt, and this nu, if you put, you will get this much only. So since they have not given H value, they have given directly H nu value. 25 milli electron volt, 10 power minus 3 electron. Okay, you can do it. You can check now. You can take H value, okay, in electron volt, and put this nu value. You will get this 25 milli electron. It will be 24.89 something. So it will give you that. So it is already given. It is already H nu is already given. What is that? 25 into 10 power minus 3 by K is in electron volt only 10 power minus 5, and T is 300. If you solve it, you will get your answer. 1. That's it for whole material science. I have put a lot of efforts. Okay. I hope it helps you a lot with the solving whole question paper, and also knowing answer key for GATE 2023. Okay. Thank you all. Please don't forget to join our Telegram channel. Okay. There I'll be giving you all the updates, like when will be the scholarship test. You can attempt our scholarship test depending on the marks in the scholarship, marks in that test. Okay, the scholarship will be distributed, like top students will be given 100% and 75% scholarship. Intermediate student will be getting 50% scholarship and 25% scholarship. So there will be huge distribution of scholarship, and it will depend on the number of students that are appearing there. So please attempt that scholarship test and join our regular batch. Okay, we together can prepare a lot better, and within 6 to 7 month duration, they can cover as much as possible. It's not possible to, as you can see, every year the questions for material science is getting so diverse. They are taking always 2 to 3 questions from new concept, at least 2 questions from new concept. So covering them all will take a lot of time, almost 6 to 7 months. So it will be really good if you join in a regular batch, and we can prepare, and we can be as stronger as possible for this great exam. Okay, link will be in the description. Just join our Telegram channel for any future update. Okay, thank you.